And say, what did she say?
She said recording in
Hey,
progress.
very excited. Okay, so I'm ready. It's a little bit early. What is it? About 5 minutes early or so? We don't care. But Dr. Green looks like he's just chomping at the bit to get someone to talk with us. So we're going to turn the show over to you.
All right. So, what I thought I'd do is talk a little bit about the latest discovery at Mars. And this turns out to be pretty significant. This is from one of the missions that I helped put together. John Grunsfeld and I made this mission happen. It's called Perseverance. So let me share my screen if I can do that. See, all right, good. Okay, there we go. Now, does everyone see one slide?
Yeah.
All right, okay. So the announcement that was made this week was about some really fantastic rock formations that can be interpreted that involve microbial life. Now, that's the kind of life we would expect to see on early Mars because it didn't have much of an opportunity to create complex life like we have here on Earth. But let me review some of the things that have been found. Well, the first thing is the setting. The setting is shown here. We have an artist's conception of the river that flows quite rapidly, many hundreds of miles upstream, and material is being gathered and brought down on in this water, and then it dumps actually into a crater. And the rover Perseverance, this is also an artist's conception at the bottom right of the image. That's where Percy is and making that discovery. So it's on the ancient shoreline of this river. Okay. Ancient shoreline of the river. So where did Percy land? Here's where Percy landed. This is a huge crater. It's on the ancient shoreline that you see in the upper right. That's where the ancient shoreline is. So in this crater, this water flows. You can see it in the upper left. It's this windy river and hits this crater, this large area, and the water slows down. And when it slows down, it starts dropping silt. This is the real reason why we went to this area, because you could see the silt. It's almost like stopping the Mississippi and looking at the result in the Gulf of Mexico of all the silt that's been deposited there by the Mississippi. This is what it looks like. If you drain the Gulf of Mexico, you'd see this material fanning out into the crater. And this was the landing area. In fact, the landing area is just outside the major part of the silted region. Now, this crater was created about 3.8 billion years ago, but the river existed many hundreds of millions of years before that. The depth is 150 meters. Okay, so 100 meters is a football field, so it's a football field and a half deep. Right where the deposits are, and most of this deposit is, since it's on the side of the crater, is about 70 meters. So the rover landed, and then it had to crawl up this whole area. Now it turns out this crater filled up so much that it broke the wall on of the crater on the other side, and that's what the outflow arrow is all about. So this water just kind of poured out, and in that direction is the ancient ocean of Mars. Okay, all right. So now we blew up here this delta, and you can see the river coming in from the upper right, going in, depositing its material, and then the yellow line is actually what Percy has traveled. So you can see the landing site, then it took off and went around a particular area. The helicopter that we brought with us took a good look at the whole area and decided, hey, this is not the direction to go if you want to crawl up the delta. So then Percy went back past its landing site and then went around this reddish area and then started climbing up the delta. Now, while it's climbing up the delta, it's taking samples all the way. This mission is designed to take samples, rock samples, okay, because it's in the rock that it tells us several things. One, what the mineralogy is. Two, what the composition is. Three, the interaction between land, air, and water, and how that forms different types of minerals. And since you're coring, you go back in time and see the entire climate history over hundreds of millions of years as you cut into this delta and get an idea what Mars was like early on until the water evaporated off the planet. Now, as it's running up, it sees this area called Bright Angel. Now, the people that name these things, and there's some crazy names all over the place, are the scientists, and they have to, when they talk, we go to meetings, they talk about well, this or that, etc. They use names, and that kind of sticks, and therefore everyone knows when they talk about Bright Angel, they're talking about an area that from orbit looks down. It's right next to the river that cuts through, and it's a brighter area than the surrounding. It's just called Bright Angel. So it's that area where we got the samples that we're really excited about. Now, here I've blown that up, and here's Bright Angel, and all this other area has these lines of material. That's actually dust. Those are mounds of dust. Mars is really dusty. Most of the dust is like talcum powder, but these dust lanes then are hugging the shores. Okay, and so we got to an area that was a little higher. It wasn't in the dust; it was above the dust, and so we crawled up it. Now, every one of these triangles is where we take a sample. Now, what do we do? What do we mean by a sample? Well, we actually core rock, and here's what a core looks like. All right, if my image is on the screen, so this is like a piece of chalkboard chalk. Okay, I can't tell if there's some really young people in the audience who don't know what that is, but it'd be like a large Crayola creme to them. Okay, and then what we do. Then what we do is we put it in a metal sleeve like this and then lay it on the ground to be picked up. Now we will hold on to these samples and then drop them in an area, a bunch of them together. And we've done that already. But here we've collected 3 samples. It Bright Angel, left Bright Angel, collected more. And this was done more than a year or so ago, probably a year and a half ago. And as we started analyzing the data, we then recognized there's some really unusual features. Now, here's the first set of features. This is a camera that looks down in an area where we're going to take a sample. And this looks like, if I showed a geologist, I may have a geologist in the crowd, but I showed this geologist and they'd be talking about how these formations are associated with water and a certain set of types of minerals. So this would be very familiar here on Earth. Well, it's not on Earth; it's on Mars. And what's really great about it is if you look right in the center between these two whitish ridges. That looked like they were, water was forming and lapping back and forth. This is clay. This is a set of clay, and in this clay are these dots. These what are called what we call poppy seeds, these dark dots, and then these round faded clays with a green exterior around them. They look like leopard spots. So there's two types of things that are in this image. And that's what got everybody excited. Okay. So here's a blow up of that area. And this has now got other instruments that are used to analyze some of the compositional elements here right over the image. And the first set is in these squares, and these squares are looking at what they call these poppy seeds. And these are just dark green spots. All right. So one of the scientists, referred to them as poppy seeds, and that's stuck. All right. And then here's one of the kinds of spectra that we take. And this G band that scientists talk about is just full of organic matter. Now that means carbon stuff, carbon compounds, things that biology loves, that biology makes, in terms of our bodies or any kind of living creatures. We're full of carbon compounds, and eats. We are what we eat. So organic carbon is really a really important element here. And then another instrument takes this red pass. So you got this organic mud with these green spots in it, and now we're going to take a different look at it with this red stripe. And the red is the rich organic mud, and it contains both the poppy seeds and the leopard spots, which are these slightly discolored mud, and then the green core around them. And the purple areas are full of iron and phosphorus, and the green areas in this slice are full of iron and sulfur. These two minerals are commonly associated with microbiology here on Earth. Microbiology eats the organic matter, part of the organic, or part of the metabolism process, extracts what it wants, and then eliminates waste, which then chemically interacts with the mud and creates vivianite and gregenite. And those two are common minerals here on Earth associated with biology. Now, it turns out you can make that stuff at high temperatures, but it turns out there's no indication that the temperatures were anywhere near as high in the entire history of Mars in this area to have been able to make that. Okay. So, the theory then is the top theory, and it's just a theory, is that the microorganisms are consuming this organic matter and died in this area, and then the results of that interaction is also obvious from and through these minerals. So, what are we going to do about it? Well, the key thing is, can we detect life from just these rocks? Okay, they're just rocks, right? Well, on Earth, there's 5,789 minerals. Okay, that means rocks with certain compositions and certain matrices. But 337 of them are made with dead life. Okay. Okay, and they're all the way from fossilized dinosaur bones that we see to these two minerals we just talked about. Those are all part of this rock record. So the idea of doing the rock record is not only all the geology stuff I talked about, Mars as a planet and how it evolved. Also, if we get lucky, we could bring back minerals where they're part of this 337 minerals and clearly indicating dead life. because there's no more life on the surface. The surface is all dead, dead life. If it's there, it's not alive. Well, we already knew a bunch of them. Now, many of these are already, and they're there on Mars, but these are also can be generated abiotically. And so you have to then put the context of the observations in terms of what it was like before the life was interacting in this area, and what it was like afterwards. So you got to look at the core. So a core is a perfect thing to do because we can see and we can age date these things, and we can see how deep these things are, whether they're pervasive in this mud, this clay region or not. I mean, there's just a bunch of stuff we can do. Well, that was what Percy was designed to do. By the way, we call Perseverance Percy, just as a nickname. And here's Percy. This is the robot, the rover, and right there, right in the lower middle part, you can see the holes that it made. All right, so it scraped away an area in the upper right, and then in the lower left, you can see the actual hole that it made. Um, and as of today, out of the 38 samples that we want to collect, 30 of them have been collected. We got 8 more samples to do, and then we've used all our sample tubes. We would be then ready to bring back the rocks. All right. Okay, so what's so important about this discovery is that here's a little background on that. For life to exist, it has to have 3 major things. It has to have water, it's got to have energy, and it's got to have organics. And the energy is sunlight. Okay. And it has to have time. It has to have time to evolve. Now, the organics in general, there's a set of things. It's not just carbon, but it's mostly carbon. But there's a set of things that are all part of the life process, and it's carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. Okay. So that's everything you get between my 2 fingers. So I'm just pulling on my skin right here. I mean, when we look at the composition of it, it's hydrogen, carbon, it's carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. So these 2 minerals that have got a ton of sulfur and phosphorus in it could have been part of the excreted metabolism process from the microbes. Okay. They had to be brought in there somehow. It's not elsewhere in the mud. It's only in these special regions. Okay. Pretty neat. All right. And then it has to have time. You have to have time to go from inorganic to organic or pre-biology to biology. You got to have time to be able to make life. That secret we don't know. We don't understand that at all. We're trying to figure it out here on Earth. We just can't pull it off. Everything we do has some nice results, and then there are dead ends. So we can't figure out how you can actually create life. Now, Mary Shelley tried, but that didn't work out too good. All right. She wrote Frankenstein, of course. The important thing is how confident are we that we found life? How confident are we as scientists? Can we really say it's life or not? Well, several years ago, myself led a team of scientists to really define what that is. And we called it the confidence of life detection. We call that the cold scale. And the cold scale really is all about if you go to level 7, you found life. You can declare you got life. Everyone believes you got life. You have all the reason to believe it's life. You found the alien you went out to look for. All right, that's level 7. And level 1 is you see what we call biosignature. Well, what could be a biosignature? Well, a biosignature could be methane. Life on Earth generates methane. It's part of our metabolism process. Okay, it's the output of our waste is gas, and that gas is methane. And we measure methane all over the place on Mars. Every day we make measurements of methane. But methane can also be generated abiotically. It can be generated with magma, which is molten rock, and olivine and water. And so there's a chemical reaction that occurs there. Methane can be created. So what's happening below the surface of Mars, we can't tell if that's it or it's really life, but we have measured methane seeping through the soils of Mars all over the place. Curiosity has been. Curiosity is the rover that can measure methane, and it measures it every day. Every day it turns on, makes an atmospheric measurement. Methane's there. Now, methane doesn't last very long in the air. It's a handful of years, and you can get chemical reactions and destroy all the methane. So the fact that we're measuring methane is probably something that's being generated more recently. That's where most of us think, or some people think that it's generated a long time ago and then captured in some chemical process called a clathrate, and then all of a sudden breaks out of that and leaks out. But it leaks through the surface. But in any event, that would be a biosignature. Now, the results that we have found we'd put it on this scale at about level 4. Maybe not quite 4, but nearly 4. If we brought the samples back, we could walk up 5, 6, and 7, or not. All right. But by bringing the samples back in our laboratory, we would have the best chance at confirming that we found life. Now, level 4 is a huge step. All the methane that we measure has never gone beyond level 3. Okay, so we never could get to 4 with methane. And now here we see with all the right composition, all the right context, everything around it, these two minerals that are associated with microbes here on Earth. Therefore, there could be microbial life on Mars. And now we've got a really good case for bringing these samples back. Well, NASA's trying to bring them back. You know, when I left Planetary, we had some ideas on how to do it, but they've been costed out, and it's been decided it's too expensive. And so we're going to bring them back when humans get there. So when humans get there, and that's upcoming, maybe in the next 10 years or 15 years, probably more likely, we'd have the opportunity to have humans on the ground. We'd be bringing the samples back prior to that. Now, why would we do that? Well, because humans, when they land on Mars, live and work, will have a Mars ascent vehicle, and they will get in it, and they will come back. And to test that vehicle, we'll have to test that at least a couple times with smaller versions of the MAV. And those smaller versions of the MAV will be bringing back the samples. So that's what many of our scientists are pushing. That's what I'm pushing. Talk about it a lot that way. And that's not cemented in NASA's plans, but we hope in this next year or so it will be. So right now, off to the left of this chart are all the assets we have at Mars. Those things that are grayed out have died most recently within the last couple of years. And the things that are active are full images. So it's Curiosity we landed at in 12, actually launched in 2011, landed in 2012. So it's been on the surface, for 13 years plus. Perseverance rover got to Mars in 21, so it's been on the surface for 4 years, doing a fabulous job. And an upcoming rover that ESA is doing that I actually, as head of Planetary, spent about $125 million for one of the top experiments that are in this rover, Rosalind Franklin. Hopefully that will go to Mars in another couple of years, and that will go down deep, many meters into the soils, and go after, maybe a source of methane, or maybe where these microbes might still be alive, because inside the crust of Mars is just full of water. Okay, so and then of course humans will go, and they'll do deep drilling, and get ice and do all kinds of stuff. So that's pretty much the story. So bottom line is, to me, um, the confidence of life detection is very high, and it's not the only one. So I think we're in an era for which we will definitively say that there's life on Mars. Uh, Personally, I believe we have found it, and we have found it a couple times on Mars, but we couldn't declare it. But to me, it's just the story is getting clearer and clearer that when life started on Earth 3.8 billion years ago, it also started on Mars. Mars was a blue planet, just like the Earth was. Now, Mars went through climate change about 3 billion years ago, and then slowly became a very arid planet. Actually, it wasn't so slowly, it occurred very quickly over tens of millions of years. That's quick to a planetary scientist. But it lost all its water. There's no water that exists on the surface anymore, but it has an enormous amount of water inside it, trapped in the crust and in the aquifers. And I think that's where the current life on Mars is at. Okay, so that's the story, and I'm sticking to it. Any questions?
Well, thank you. Questions?
I don't know how many rock samples you've been able to do over however many years. Quartz is basically the most abundant on Earth. How does that compare to with Mars?
Yeah, we've seen quartz. We've seen quartz. Right now, we have a tally of probably close to 300 or so minerals. We haven't been everywhere on Mars we'd like to go. We've only been to a couple places where we actually can do the analysis and understand what the mineralogy is. Unlike Earth, here on Earth, we've pretty much been everywhere, and digging up all kinds of stuff. And so that's why we have a much larger collection of minerals. So the key for us was, well, let's go to those areas where we know or believe that water existed on Mars in the past, and then look for those minerals where there's been water, land, and even atmospheric interaction to be created. Like hematite. We see hematite all over the place. Well, hematite is iron in water, and so even on some of the plains area, there must have been a lot of water, rain, and puddles, and all kinds of stuff over the years that then created the hematite. Because Mars does have a patina of iron. That's why it's oxidized now, and that's why it gives you that reddish color. But we don't have a totally good catalog of the mineralogy. Bringing the rock samples back will be different. We'll actually probably increase that by a couple orders of magnitude. Maybe getting it up to a couple thousand, many thousands of minerals, because we can go inside the rock and look at it over time, just like we can here.
Hey, Rob.
Good question. Anybody?
If you had the chance.
Would you sign up to go?
To analyze the rocks? Sure. Well, if you meant to go to Mars, I'm not a young scientist anymore. I mean, if I had one scientific wish, it would be that I just graduated from the University of Iowa at 29, and I was ready to start my career like I did in the past with the knowledge that I have right now. Okay. with a career's worth of knowledge. Then I would probably consider going if given the opportunity. But I'm not like Elon Musk. I don't need to die there. Things that I've been involved in have been there and are there now. Percy is a rover that I helped create when I was at headquarters. Now, what do I mean by that? Well, it means I'm working with JPO and the science community on the concept of coring rock and bringing it back. Well, how are we going to do that? Well, we're going to build a robot to do that. Well, it's got to have wheels. It's got to have a coring machine. It's got to have instruments on it that can give us the indication of, oh, let's go here and core, not over there. Okay, so you have to have all these other instruments. So by putting that idea together, we then could cost it. And then once we got it costed, it was my responsibility as head of planetary to sell the idea, not only because it's already sold by the scientists want it, but I have to sell that idea to my boss, who was the associate administrator of science, that we needed new money to get this, new money to make this happen. And then I got to get the administrator on board, and he's got to say, yeah, NASA's going to get their full weight behind this idea and go to the president and the Office of Management and Budget. You got to get the money, they got to give it to us. And they're cheapskates. They're tighter than bark. And then you got to go to the president's science advisory group, the Office of Science Technology of the President, OSTP, and they got to get on board. So, and then if you got all those okays, you then can go to Congress and ask for the money. Well, Congress could still say no. So there's like 6 steps, and so the stars all have to line up to get it. All right. And in the 12 years I was planetary, I did that for a bunch of missions. Curiosity, all right, Perseverance, the DART mission, which we used to hit and move an asteroid, what's called the CLIPS mission, which is a series of missions to the moon, and then the Europa Clipper, which is going to Europa. And it's all those are done. All those I got new money for. We created them. When I get the money, then I can give it to JPL and they can build it. They can't get the money. That's not their role. It's my role. All right. Everyone depends on the division director to make this happen, or your field doesn't go anywhere. You don't get. No one else gets the opportunity to sell this idea. It's just one person. That's the division director.
No pressure.
So, no pressure, right. Well, I was tremendously successful. Typically, a division director gets one of their choices as a new start. This is called a new start because you're going to start something new. You need new money. All right, new start. But you get one a decade. I got 5 in 12 years. So I was tremendously successful. And part of that is because what we're doing in planetary science is not only really exciting and I think historic in many different ways. It really has changed the way we have viewed life here on Earth. When I graduated at the University of Iowa, there was no hope of finding another planet around a star. Just forget that idea. Never will happen. Well, we figured out how to do it. In my lifetime, we figured out how to do that. And there's some really neat ways to do it. We get telescopes that make those measurements now. Totally unheard of when I graduated. And now we know there's more planets around stars than there are stars. Wow. All right. And we didn't know when I graduated at the University of Iowa what really killed the dinosaurs. Why did they come and go? We didn't know much about the 5 mass extinctions that have happened on Earth. And now we know. And at least one of them is due to asteroids hitting the Earth. That's why I started a program to go find them. So, and then after we started finding them, I recognized, we're in a horrible orbit. stuff flies by us all the damn time. And we figured out we needed to track about 60,000 near-Earth objects. All right, 60,000 that cross our orbit and can hit this planet and affect life on it in significant ways. All right. And it's not a matter of if, it's only a matter of when. The fact that they're distributed over a large area is tremendously helpful. And they keep missing us. We now know that over the next 100 or 200 years, we're okay. But after that, there are a couple that we really have to watch out for. Okay. In fact, we didn't really think about this as objects like asteroids coming from other solar systems that have escaped. We now know that happens on a regular basis. We now know the population of asteroids comes out of the asteroid belt, and it's being pushed out of the asteroid belt because of Jupiter. Jupiter gravitationally interacts with the asteroid belt, throws asteroids out of the solar system, or throws them inward. And if Jupiter throws them inward, they become our hazard. Well, right now there's at least 1 million asteroids in the asteroid belt that Jupiter is messing with. All right. So the concept of not only watching out where these 60,000 asteroids are is important, but we got to keep doing it. We can't let it go. It's going to be an occupational hazard for life on Earth to see these things. Now, once we started that process and we started seeing these, measuring their orbits and knowing where they're going, the question is, well, okay, now that you know they're there, how are you going to defend the planet? Wait, what are you going to do? How are you going to stop this rock that's going to come and hit the planet and kill most of the life on it? What are you going to do about it? Well, the dinosaurs didn't have a space program. All right. We do. And so we better figure out some space scenario to do that. And so that's where we came up with the mission DART. So DART was a great idea. It's taking a spacecraft, and hitting an asteroid and seeing how we can move it. And we did all the calculations necessary to figure out, well, we think we can move it by this and do that. But that's all theory until you actually do it. So I got all the stars lined up, and I got money out of Congress, and we got the thing built, and we fired it at an asteroid called Didymos, and we hit it, and we moved it. In fact, we moved it more than we thought we could. That's really good news, because that means we then can size some of these systems such that we can move bigger and bigger ones. Can we move them all? And the answer is no. We haven't figured out how to move the really big ones. All right, so I'll give you an example. The one we moved was 160 meters. Okay. That's less than 1/5 of a kilometer. There's a couple near-Earth objects that are huge. One is 33 kilometers. 33 kilometers. We only moved one, a fifth of a kilometer in size. So how are we going to move these really big ones? And we're going to have to figure that out, because we know out of the 60,000, there's about 1,000 of them that are really big. Those are the ones we're trying to figure out the next thing to do. And then all of a sudden we start seeing these coming from other solar systems, flying through our solar system, which is the Atlas III one that is flying by us. And it's really moving. The problem is it's not very big, but it's really moving. I mean, 50 to 55 kilometers a second. Now, wouldn't you like to go to Iowa City in 3 seconds? All right. Well, all you have to do is hop on one of these and you're there. As soon as you get on, you'll have to get off. So that's really moving. We can, when we leave the gravity bounds of the Earth, it's 11 kilometers per second. We can do that. When we leave the gravity bounds of the sun, it's 14 kilometers per second. This is 55 kilometers per second. We don't have anything that can run it down, land on it, or anything. The only thing we could do is try to fly in front of it and let it hit it. That's the only thing we could do. And we're talking about, I'm retired, okay? I'm no longer in the middle of making this happen, but so many people are really working hard to make these things happen.
Good. Any other questions?
I'm gonna go back to rocks again. Why not?
Can you hear her okay, Dr. Jim?
No, I can't. No, I can't. What was the question? Can you repeat it?
Okay, I was asking about how Mars rock population compares to Earth. I was wondering about the moon, since that's been more studied, how that compares to the composition of Earth.
Yeah, really good question. Well, we brought about 850 pounds of rocks back from the moon. The samples that we're creating will probably bring back a couple pounds, okay, if that, out of 30 samples. But we brought back so much material from the moon that we did really detailed analysis of it, and we still are analyzing moon rocks, but it tells us that all the stuff on the moon is the same stuff as on the Earth. So the Earth and the moon were created at the same time. Okay. And so what was happening is material was accreting 4.5 or 6 billion years ago to become bigger and bigger objects. And something we think the size of Mars and something close to the size of the Earth, what you call the proto-Earth, and the other object is called Theia, collided. And in the end result, we created a bigger object we call now the Earth, and a much smaller object than the original Theia that turns out to be the moon. So then that became locked in orbit around the Earth, and the Earth didn't have the ability to pull it in. And in fact, we now know the moon is actually moving away from the Earth an inch every year. Actually, it's about an inch and a half every year. Okay. And so the Earth's day is slowing down. All right. So you can imagine a ballerina spinning, and she's got her hands in, she's spinning very fast. As she pulls her arms out, she slows down. All right. So as the moon moves away, it's the same basic concept. To conserve angular momentum, the Earth has to slow down. So our day is gonna get longer. It turns out the moon is 360,000 kilometers away. So, so an inch and a half isn't any big deal, but it's almost measurable. We can almost measure the change in the day. By the time the moon gets far enough away, escapes from the Earth, that'll be 5 billion years. Okay, so we're not too worried about it. But it is an aspect of the Earth-Moon system. Without the moon, life on Earth would be very different. All right? Very different. We'd have much larger climate change excursions. Our rotational axis would be flopping around all over the place. Right now, we're pretty steady at 23.5 degrees. We only actually move a little bit. This is called obliquity. And so the obliquity of Earth right now, 23.5 degrees, but it used to be 24.5 degrees. It's coming off 24.5 degrees. It's going to go 22 degrees, and then it's going to go back to 24.5 degrees. And it does that over about 100,000 or so years. And that's what's called a Milankovitch cycle. So we're all scientists are all pretty familiar with these kind of concepts, that that the importance of the moon has enabled the Earth to have a moderate climate as we do.
I see, let me just double check.
I got my hand raised because I went like this.
Oh, okay. I was wondering, Percy, do you know how much longer? It's doing great, right?
Yeah,
So,
Percy's doing great. Now, Percy has a bunch of instruments on it that are really quite unique. So even after it gets all its samples made, we're going to want it to keep going and view more of the mineralogy on the surface. We think we'll find more areas like this, and the more areas like this we find under similar conditions. If we found this kind of area out in the middle of the desert, we'd say, okay, it's probably not life. We better figure out what it is. But it's in the shoreline of an ancient lake. All right.
Mhm.
This is where the
Contact.
microbes would be.
That's so
You know,
cool.
so that's why the level of confidence, the confidence of life detection is as high as it is.
Exciting.
But as I say, personally, NASA will never say this. I think we found enough evidence to say that Mars had life in it. Now that means, even though it's microbial life, that means that life's all over the place. That means there'll be planets that will be Earth-like with oceans and land that may have a significant amount of oxygen that allows for different types of life to exist. The key is now, what kind of life are we talking about? Does it have the same basic DNA structure? It's got to have some sort of form like a cell. So what's that like? And it's got to have some sort of way to bring in material that it can consume, and then some sort of liquid to get rid of that, and that's part of the metabolism process. So life has three attributes to make it general. The general definition of life. Okay, one, it metabolizes, which means it brings in food with a solvent. In this case, it's water that breaks apart the food, takes material it's going to use, and then the water is used to eliminate the waste. That's a metabolism cycle. So metabolizes. Second thing, it reproduces. Third is it evolves. That's it. If we see something with those three attributes, it's life. The problem is, those are really hard to measure. What we're seeing in the rock is, we think, the metabolism process. All right? Because we see it also on Earth, and we know we can point to it in an area where there was water, in an area where there was food, organic material. The mud is full of organics. That's where the food is. Okay, and so it's all connected very nicely. That is the context of the sample that raises it up to a higher level. And now it's level 4 is because we can't think of anything else. There's not. This has been known for a year, and the scientists have had a paper out, scientific paper that was under review. There probably was 10 reviewers on it. 10 of the most skeptical reviewers that want to absolutely disprove that this is life, and they couldn't do it. Okay. Now that doesn't mean there's the real explanation is life, but to me, if you got the smartest minds in the world working on this, and they can't come up with anything better, I think we have a really good shot at it being life. Now,
I wish, yeah.
the key to
I wish,
that is
yeah.
having it in the lab, and then we'll know.
I wish Carl Sagan could be around to hear
Yeah, I
all
know. Yeah, I know. Yeah, I agree.
We might-
However, I would have one bone to pick with Carl.
Okay.
Okay, you want to know what that bone is?
Yes.
Carl said very famously, if we find Martians on Mars, we need to leave Mars to the Martians. And I disagree. I disagree.
Fair enough.
And part of that is because he felt that we couldn't handle another set of life in another in a planet and preserve it. And yet we are the only species on this planet that care about other species. Really. I mean, there's some symbiotic relationships, but I mean, really care about other species, care about extinctions, worry about deforestation and the extinction of certain species that are indigenous to that area. I think we can go to Mars, and if we find life there in the aquifers, we can live together. In fact, it may be the conditions on Mars are getting more and more harsh, and that maybe life on Mars is on its way out. It's eventually going to die out. If we go there and we find life, what are we going to do? Well, we're going to terraform Mars. Mars is going to become more Earth-like. The pressure is going to increase. We'll have water on the surface. We'll plant food. We'll have Earth life on Mars, and we'll be bringing Mars back to when that life grew and survived and thrived. So I think the best thing to happen is, if Mars had life, is that we go there and that we find it and we work together. I think we can do that.
Sounds
If
like
we can't do that, no other species is going to be able to do it.
sounds like some good movie plots there.
Sure, probably. Oh, by the way, go see Hail Mary.
Oh, Mary, I'm not familiar with it.
Yeah, Hail Mary is out, or should be out pretty soon. It's a new science fiction movie by Andy Weir. So if you like The Martian, you'll like Andy Weir wrote The Martian. You'll like Hail Mary.
Thank you.
Sure.
I'll do that. Well, we're kind of bumping up, I think.
Yeah. Well, we sure do appreciate you being here and
My
sharing
pleasure.
with us, and looking forward to you doing it again sometime.
Absolutely.
Well, thank you so much,
Absolutely.
Dr. Green.
You're
You take
very, very
care.
welcome.
Thank you.
Bye now. Thank you.
Thank you so much. Well, I think we are done for the evening. So